Hey all, today we're going to continue our discussion on similarity, and we're going to talk about similarity in right triangles specifically. So before we get there, I want to talk about this idea of geometric mean. A geometric mean, by definition, is a positive square root of the product of two numbers. So that means if you multiply two numbers together and take the square root, whatever that value is called the geometric mean. There's a couple ways to find what geometric mean of two numbers is. So if I want to find the geometric mean between 2 and 4, I'm going to call that mean x. I can write a proportion, 2 over x and x over 4. And so what I get when I cross multiply is x squared equals 8. And then x equals the square root of 8. So it is the square root of the two numbers multiplied together. So we can sort of skip that step in a way and just write the geometric mean as the square root of those two numbers multiplied and get the same value. It's important to understand that we can do this as a proportion. As you might guess, we're going to be doing that with some triangles. We've been writing lots of proportions so far this unit as triangles are related. So let's do a couple examples, and I'm going to do both methods. In terms of a question like this, you can choose the method you like best. So we could write a proportion to find the geometric mean of 5 and 9, 5 over x, x over 9. Or we can just say that is the square root of those two numbers multiplied, which is root 45. Same thing here. I could write a proportion, 6 over x and x over 12. I don't know if you notice a pattern. I take the smaller number, divide it by x, and then x is on top of the bigger number. Or x is equal to the square root of those two numbers multiplied, which is the square root of 72. And I'll do one more. 1 over x, x over 7. Or you can just do the square root of 7 times 1, which is the square root of 7. So these square roots here, these x's, all represent what we call the geometric mean between those two given numbers. So now let's talk about similar right triangles. And we have this special case scenario where if we have a right triangle, so I have this big right triangle ABC, this big guy. And then I have what's called the altitude. So if I have the segment in this right triangle that starts at the vertex that's 90 degrees and is perpendicular, making right angles, to the hypotenuse, that's called the altitude. And I hope you notice that inside this big right triangle are two smaller right triangles, one over here and one over here. And all three of those triangles are similar, and that's what this statement says right here. So this special similarity occurs if we have a right triangle with its altitude drawn. We now have created three similar right triangles. And so on this page here, I've pulled those triangles apart. And this might look a little bit like a mess right now when you start looking at it right away. But here's my original triangle, triangle ABC. And here's one of the smaller triangles. I'm going to call it the medium triangle, ABD. And then here's the smallest triangle, BCD. And in each of them, you have a hypotenuse, and you have a short leg and a long leg. And so we can write all these different proportions using corresponding parts. So for example, I could write a ratio of the hypotenuse of my original triangle over my hypotenuse of my medium triangle and make that equal to the short side of my, I'm going to use a different color, the short side of my original triangle and the short side of my medium triangle. So we can create all these different proportions if we if we write ratios of corresponding sides, so like hypotenuse to hypotenuse, short side to short side, long side to long side, the possibilities are endless. Not really endless, but there's a whole bunch of them. But what we end up with is this altitude actually, this altitude BD is actually the geometric mean between the long side of my medium triangle and the short side of my small triangle. So again, let me say that again because it was kind of broken up with me clicking. The altitude is the geometric mean of the long side of my medium triangle and the short side of my small triangle. Put another way, the altitude is the geometric mean between the two pieces that we break the original hypotenuse up into. So we have this relationship, just like we wrote the geometric mean a couple slides ago. Small number, DC, over geometric mean equals geometric mean, BD, over big number, AD. And so that is the very special case, the very special proportion that exists. But like I said before, there is a whole bunch of proportions we can use when we're presented with a scenario like this, and it's kind of helpful to find missing sides. So let's do that. There's my altitude, and then my original hypotenuse gets broken up into these two segments. And so y is the geometric mean between these two segments. So I'm going to write little side over geometric mean equals geometric mean over the bigger side. And I can solve that and get y to be the square root of 48. And then we also have this relationship in order to find uh, x. This is the hypotenuse of my little side. And then I have the hypotenuse of my big side, which is 16. So I can write a fraction, x over 16. And then I know the small side in my little triangle is 4. And I could divide that by the small side in the big triangle, which is also x. So we get this proportion that we can solve and find x to be 8. Let's do another one. Again, y is the geometric mean. It's the altitude, so it's the geometric mean of 4 and 5, the two parts of the hypotenuse that are formed by the altitude intersecting it. So I could write 4 over y equals y over 5 and solve to get y to be square root of 20. I also have the hypotenuse of my smaller triangle, and I can divide it by the hypotenuse of the bigger triangle. And I have the short side of the smaller triangle, and I can divide it by the short side of the bigger triangle, and I can get this proportion, x over 9 equals 4 over x, and get that x is to 6. Now, once you find x or y, depending on which one you find first, there is another way to find the second variable. I don't want to go through it on here, but it's a totally acceptable way, and I'm curious to find out who figures out that way, because maybe it's a little bit quicker. Let me do one more with you. Y is the altitude, again, so that's the geometric mean between 21 and 4. And so I can write my proportion, 4 over y, small over mean, mean over big. Solve that to get y is root 84. And then, again, x is the hypotenuse of the small triangle, so I compare that to the hypotenuse of the big original triangle. 4 is the short side in the small triangle, so I'll compare that to x, the short side in the original triangle. And I'll get x to be 10. So I want you to try this one. Try this one on your own, and then I'll reveal the answers. And if you have questions about it, ask me in class. I'm not going to go through the answer, but I'll reveal the answers for you so you can check them. So if you got root 63 and 12, that's great. If you didn't, that's okay too. Just make sure that you see if you can find your mistake. And if you can't, make sure you remember to ask in class and I can help you find your mistake. Again, if you have any questions, make sure you write them down so that you can ask me in class.